All right, thanks everyone for coming. So I'm going to talk about the work I'm doing in my PhD, and this is work with all those people, Yizu, Basili, and Eric, who are all at Stanford with me, and then Chao Chen, who is now at UT Austin, and then Eric Bowman, Siva, and Ray, who are at Sandia. So the context is, I think, something we pretty much everyone does here. So we're just trying to solve large, sparse linear systems, who we assume come from some sort of PD discretization. And we're trying to build some sort of generic and algebraic algorithm. So in the sense that it's not fully geometry-based and scalable. So typically multi-level and some sort of linear or near-linear complexity. And finally, and more recently, we're interested in trying to do some sort of parallel task-based version of that algorithm. And so I'm going to talk about that. So first, just to, I guess, maybe refresh everyone's mind, but I'm sure everyone knows that to some extent. So the classical, simplest way to solve linear systems is with a direct method. And in the sparse case, you would do something probably like nested dissection, in particular for like physical problems. And so the way it works is you basically need to build separators and interiors. And if you keep doing that, and you eliminate interiors, recursively somehow, you end up doing something that looks like this. And in the end, you've eliminated a bunch of things, but you are left with one really dense matrix, the bottom right there, whose size is the size of the largest separator, right? The largest separator in your problem. And so that's fine. The issue, of course, is that that doesn't work very well for like typical 3D problems, because your top separator looks like a plane, and a plane has size O of n to third, and then you need to eliminate that. And at this point, that's a dense, full giant matrix. So that's quadratic. And so that's really the main reason why direct methods are slow. It's because in 3D, separators are very big, and so they end up being quadratic. It's better in 2D, but in 3D, that's the issue. And in higher dimension, it's a nightmare. So our goal is mainly to try to address that. The main goal is to try to reduce the size of this large top separator somehow. So how do we do that? So let's take a very simple problem first. So I'm showing like regular problems. It doesn't have to, but that makes plotting and understanding a little easier. So imagine you have on the left is the matrix graph, but just a bunch of sets. Okay, so this is not like every set is a set of nodes in the graph, a bunch of rows or columns in the matrix. And so you have kind of a hierarchy of separators. And so the first step you do in every nested dissection is you eliminate interiors. So if you eliminate those 8 big interiors, you go from the left to the right. And so on the right, you are left with separators, of course. But of course, now there's a lot of fill-in, right? Between this one and this one, there used to be not that many connections. But now, of course, there's a lot of fill-in. And this fill-in is the reason why it's slow. So what we propose to do is basically take that fill-in and approximate it with some low-rank approximation. So if you consider this piece here of this larger separator, we call it an interface. Well, you basically take all its edges to all its neighbors, and you do a low-rank approximation. And basically, because this is fill-in, the low-rank approximation makes sense. If it wasn't fill-in, typically it doesn't work. But because most of those connections from P to the others are fill-in, it does work. And so you end up, you start from the left, you eliminated a bunch of interiors, and now you do those low-rank approximations from here, and you basically drop the low-rank part, right? So you have all this, you do a low-rank, and you're going to drop this thing. And basically, effectively, when you do that, you reduce the size of all of those interfaces by a bit, typically around a half, somewhat. So that idea, I have to say, was from this paper here from 4 or 5 years ago, from Lexing and Kenneth Ho. And we're trying to expand that idea to more general problems, basically. So that's the main idea. You eliminate interiors, then you are left with a bunch of interfaces, and then you're going to make them all shrink by something. And you do that with low-rank approximations. So effectively, if you look at the top, when you do that, you start with your matrix on the left. The I are basically the rows and columns of that piece, the P that I had here. Then you apply those orthogonal matrices, and you end up with the right. And on the right, a lot of rows and columns are small, and so you just drop them. And you move forward with a smaller matrix. So one question is left is, what piece do you actually sparsify? So imagine this is again some sort of matrix graph, where I just show like clusters. It's not the matrix, it's the graph of the matrix. And so traditionally, if you do nested dissection, you have a top separator, and you have lower level separators. And the way we pick those blocks to sparsify is, you give numbers to all of those guys, and then you cluster together those that have the same left and right neighbors. So if you look at this, for instance, those nodes here, they have the same left and right neighbors because they touch both 3 and 6, and so they kind of get clustered together. And you do that for everyone, and you end up with those kind of clusters on the left. And then, of course, you do that in some sort of, like recursively at all levels of your nested dissection tree. And so finally, if you do all of that, it's going to look like that. So imagine on the top left, that's your original graph of the matrix. The colors represent the level in the nested dissection. So the green is your top level separator. The red are the level right below. Then the blue and the white are your leaves. And so you cluster in the way I just said. You basically cluster together those with the same left and right neighbors. And then you do this three-step thing. Eliminate your interiors. Scale everyone else, mainly because it's very good for accuracy. And then sparsify, and then repeat that at the next level. So you start here. You eliminate all your interiors in white, so you end up with this. So now you have a lot of fill-in, right, between those guys here, those guys, etc. Now you take all your clusters here, you scale them, which we can kind of forget for the purpose of this talk, and then you sparsify. So you do this Lowrank approximation. Oh yeah, sorry. Does this? Oh yeah, okay, nice. Right, so you go from this, you sparsify everyone, and then you basically merge and kind of go to the next level of your hierarchy, and you keep doing this. And effectively, when you do that, you reduce the size of everyone step by step, and at the very end, your top separator, which was potentially very big, remember, like n 2/3 in 3D, becomes much smaller. In terms of the matrix, it kind of looks like this. You start with your matrix, which you may remember, you may notice some sort of nested dissection. You eliminate all your interiors, so it's smaller but denser. And then you take everyone, you kind of scale them, and you sparsify, which effectively you make a lot of rows and columns 0 or small, and you just forget them, and then you just keep doing that. You go to the next level, you eliminate, you scale, you apply, you compute and apply those orthogonal transformations. Bunch of rows, columns become small, you forget them, etc., etc. And at the end, this block hopefully is a lot smaller than it would be otherwise. I'm going to skip this. So an important question is how much smaller? So typically in 3D, imagine this as a piece, a piece of this graph I had at the very beginning. It's like, oops, yeah, it's like, you're like here. It's like this thing, a view of this. Oops. There you go. Oops. So, you start with this, and you just eliminated what's on the left and right. Okay, you eliminated all of those guys and those guys. And so at this point, if you look at this cluster, basically, most of those nodes are connected to this and that and that and that only through fill-ins, which I don't show here. But basically, the point is that fill-in in general spacifies well. So fill-in is very low rank. What's not low rank are the connections to those guys right here, because those are original connections in the matrix. And so what you can say basically is that you will be able to specify most of these, but not those. But so what it means is that you go from planes, because this was originally a plane, you go from planes to lines. And so roughly, the separators will go from 2/3 to 1/3. That's the main point. And 1/3 cube is only O of n. And so that's why the algorithm is, if everything goes well, about n log n. Because at the beginning, you have a bunch of leaves, so O of n clusters of size O of 1, so that's O of n. And at the end, you have one separator of size n 1/3, so that's O of n to factor. And so you can hope that the algorithm will be n log n of course, if this happens. So some result quickly on this, and then I can talk a bit about the parallel version. So this is showing actually the separator. So this was the original nested dissection separator on this kind of 3D Poisson-like problem. And this is the size after sparsification. So it's a lot less. And this actually scales pretty close to n to the 1/3. So with this is for like a given accuracy in your Lowrank, and you end up with like around 15 CG steps. So it's pretty accurate. And you see that the factorization time is it's not exactly linear, but it's pretty close. It's far from quadratic. A different problem. So this one is more like a 2D because it's pretty thin. And so here, yeah, the separators are around like they grow very slowly. So when you refine a 2D problem, in 2 dimensions, typically your separators grow very slowly. And here they grow by actually very, very little. And so this shows again like the factorization time and the solve time for, this is O of n, so it scales pretty well. And this is the memory. And I just want to mention that this trend of, n 1/3 separators versus n 2/3 as, in the section holds for non-elliptic PDEs as well. Not all of them, far from it. But as far as I can tell, it holds for more than just, elliptic PDEs and SPD matrices. Those are some indefinite symmetric. Those are some unsymmetric problems. And in both cases, I see similar trends for the top separators. Okay, so that's overall the algorithm. Now I want to talk just a little bit about how we try to parallelize that. So we're trying to use some sort of task-based approach. And to do that, we built this, pretty small, but this library that we call TaskTorrent. So the goal of TaskTorrent is basically to build, to have a very simple task-based runtime. And so, the main idea is you have tasks, which are like nodes in some sort of graph. And, tasks trigger more tasks. So for this task here, it needs something from this task and this task to run, and then produces, well, nothing for this one, but this one here, when it's done running, produces, kind of triggers more tasks. Okay, so that's the general philosophy. So in particular for our TaskTorrent library, so we use what you call like a parameterized task graph approach. So that's pretty important because that's a big difference with other runtimes and similarities with other. So the main idea of a parameterized task graph approach is that basically tasks are kind of nodes in a graph, but are indexed by some k, and are basically some function of k. So a task is going to be a function of some index k, which can be an int or a tuple of int or something like that. And then you describe them basically just using functions. So for instance, this task k has 2 dependencies. So you're going to express that by basically building a function of k that returns how many dependencies that thing has. Then you're going to create a function that do something when this task has to run. And then finally, you're going to create a function, you put it here too, but that triggers more tasks when that task is done. So that's the main philosophy. Really, you express things with functions of some index. And so tasks, when they are done, they can fulfill other tasks, either locally, just saying them, okay, you're ready, just go. The data is already there. Or they can trigger tasks remotely, like on other nodes, basically, by sending some active message, basically. So you send some data and some function that arrives on the other side and then triggers the task and copies the data somewhere. So for instance, here, that's what we do kind of here. When the task is done running, it triggers another task like locally, and then sends a message somewhere else to trigger another task with some data. And so this is all done completely like asynchronously in a non-blocking. And on the other side, there's no one waiting. When the data arrives, when the message arrives, the function runs, and then triggers the task. So this parameterized task graph approach notion is pretty important because that means that you never need to enumerate your tasks first. Basically, when the task is done running, it kind of triggers more tasks, but you don't need to first build the whole graph. First, basically. Oops, sorry. And Yeah, so the main thing is that you end up with a code that looks kind of very different from what you would have in a more like sequential code. If you write a sequential code, it's a bunch of loops or something. Here, your task is a bunch of functions of some index, so it's very like implicit in some sense, which makes it somewhat weird. So I just want to mention kind of the differences with other runtimes. So for instance, like in StarPU, you have more like a sequential task insertion. You basically go through your tasks, and then StarPU infers all the dependencies. That's somewhat similar in Legion. Parsec, on the other hand, is much closer because it's also like a parameterized task graph approach. You write function of k, so index, and that's how it's expressed. And well, Leopold doesn't really have. And finally, some results using that. So here, this is a very simple, like kind of dense Cholesky application. So if you do like a dense Cholesky, you basically block your matrix, and that creates a bunch of tasks, and then it ends up looking like this. So like this pot, when it's done, triggers some triangular solves, which triggers some gems, etc. And so here we did an application and a comparison, but an application on that, on dense Cholesky, using task torrent. And we just compare with StarPU, not so much for saying that it's like better or anything. I mean, it's pretty different, just to show that it's somewhat comparable. So it's not very big. It's not Exascale yet, but you see that for reasonable block sizes, meaning task sizes, they have like comparable performances, basically. I'm gonna skip this. Okay, and finally, I want to show how you would do the span diagram, so the thing I talked in the first part on that. I don't know, how much time do I have left? Not long, I think. 1 minute, all right. 2 more minutes, okay. So basically, in this span diagram, you need to do 3 things. You need to eliminate a bunch of interiors, and then to sparsify the remaining interfaces. So elimination is basically like a block Cholesky. You have a bunch of pivots that you need to do Cholesky on, they trigger a bunch of triangular solves, which themselves trigger a bunch of gems, so fill in. So that's pretty normal, I guess. Then you have this pacification part and the scaling part. The scaling is, again, very similar to a block Cholesky. So you scale the pivots, and you do a bunch of triangular solves. But then, that's the important bit. So when you want to specify this block, for instance, let's say this guy, you need all of those to be done. So you need this, this, and this to be done. Once those are ready, you can take all of those blocks, build a QR, build a basis for it, basically, an approximate basis. So you do that for everyone. And when those are done, you kind of scatter the basis in your row and column to shrink the blocks. That's the important bit. So this queue is kind of smaller. Those queues are smaller. So this product is basically a smaller matrix. And so you do that on all of them, and basically all your blocks shrink by a little bit. And, well, that's mainly what it is. And then, you just recurse at the next level. So this was at a given level, then you go to the next level. And if you kind of try to plot it, the graph kind of looks like this. You have a bunch of eliminations, which kind of trigger each other. Once those are done, you start doing a bunch of scalings, like block scalings in your matrix. And finally, when those are done, you end up doing a bunch of sparsifications, which are by far the most expensive thing to do. And those are like very, very preliminary strong scaling results. So in blue, that's basically the sequential one core, one thread, couldn't do more sequential algorithm. And then in really other colors, you get more cores and nodes. So in gray, it's just a 4 cores, 24 cores. Sorry, 24 cores on 4 nodes, strong scaling. And I end up with like 30x-ish speedups. So not 100, but as a first try, it's not too bad, I guess. So yeah, you come from basically 15 minutes to 35 seconds for the factorization. And this is on a cubic, basically a cube problem. So voila, and the main thing, so yeah, so basically what I showed is kind of this new algebraic algorithm that works on a relatively large class of problems. And we have a kind of preliminary task-based version. And our future work on that, basically there's still a lot to do here. First, the partitioning is very naive, so you end up with quite a lot of imbalance near the top. So that's something to improve. And we need a more scalable way to do those large blocks. Because this is going to scale eventually, okay, but the top, you only have very few tasks. And those tasks are basically ranking in QR, so I need to find a way to make that somehow faster. Because eventually this will become the bottleneck. And voila, I think that's it. This is the original paper on that ID. This is what we have, which is going to be in SAMAX soon. And yeah, voila. Thank you.